So thank you. I would like to share a paper currently in review on monthly weather review. My co-authors are Jeff Anderson and Laurent Bertino. We're trying to solve here reduce non-Gaussian errors in the forecast due to position misalignment and position errors. And this is using a multiscale alignment technique that I introduced in 2019. So the schematic description of this approach is instead of running the ENKF with just the input of a state X and the observation Y to obtain increment delta X, we augmented the algorithm in this scale looping iterative method. So we break the state X with bandpass filtering into different scale components indexed by S from 1 to NS. So this bandpass scale component is now considered the prior, and then the observations can be either filtered or unfiltered. Then this observation and state pairs are sent into the ENKF. Now we have this analysis increment for one of the scale component, and now we can do a little bit of alignment technique to figure out the position errors from this component, and then added the analysis increment and position increment to the prior state. Now we have iteratively corrected the prior intermediate steps, and you will use this as a new prior for the second scale component, and so on and so forth. So mathematically, this corresponds to augmented cost function minimization problem. So instead of modeling the forecast error with the simple Gaussian variable, we model the prior error model as the truth plus. So the prior is equal to the truth plus the displacement error and plus the residual error, which corresponding to adjustments in the amplitude. The displacement can be done by having the prior state in a horizontal field. Then you do some displacement, which means warping the coordinates in this image or in this horizontal field to have this update the state. And the residual, of course, is the warped image subtracting the truth. And we assume that the residual is still a very good fit to a Gaussian random process, but the random process has this covariance matrix that's conditioned on the displacement vectors. The Bayesian formulation is not that different from the original one, but we introduced this Q as the vector field of displacements. So now we are co-minimizing co-maximizing the posterior likelihood, posterior distribution with this both state and the displacement vectors. The cost function now has additional term. So the first term is still the observation mismatch, but now the state has this additional nonlinear warping inside of it. The second term is still the prior distribution of the residual error, which is still a Gaussian function. But additionally, we have some constraints or regularization on the Qs, which means we don't want the displacement vectors to be either too much close to zero or too big. To solve this minimization problem, we take a two-step approach similar to what's introduced in Ravila et al. 2007, and also later in the feature alignment techniques by Tom Nerkom. So first we fix Q to 0, and then first we fix the states, the X, and we try to solve for Q. And afterwards, when we have the Q, we fix Q and minimize the cost function again with this to solve for X. So this is a traditional ENKF update step. So why do we need this? So this extended multi-scale DA formulation allows us to do more things than the traditional approach. First, this rho function is localization, and we can localize the analysis for different scales separately. This is a very early idea by many researchers on multiscale DA methodology, and some of them call multiscale localization. For example, Brunner and Shrieva, including myself, we all investigated how to localize differently. Mainly that the larger scale components will prefer a longer localization distance, which makes a lot of physical sense. And second thing to do, of course, is what I just introduced, the alignment steps. This alignment is trying to figure out those displacement vector, and I typically employ an optical flow algorithm to derive the displacement vector field Q from the delta X. And then we add some residual error back. And thirdly, I think the observation error inflation is another interesting place to look at. So when you have this observation that contains information at a certain scale, and you want to utilize these observation to constrain model state at another scale, for example, and there will be some mismatch because of you don't have the corresponding scales in these two information sources, and that can give rise to representation errors. And recently, I also investigated how these representation errors can be addressed by inflating the observation error variances separately for each different scales. So in this talk, I would like to further illustrate how the MSA method works in a different test case. And we try to stress test the new method, because in the more difficult test case, we found more issues, and try to address them and improve the method. So the test case is a two-dimensional vortex located in the center of a square domain. Here I'm showing the U wind, so horizontal wind, the U component. You see that there's a very regular vortex in the center, but also you have some random background steering flow added on top of it. And on the left-hand side, I'm showing the kinetic energy power spectrum of the wind field, and showing the 4 different scale components as an example. So this problem is quite typical for a non-Gaussian test case, because when you displace the vortex in the horizontal position, you will have a very non-Gaussian prior distribution of the error. So here, to illustrate, I'm increasing my ensemble spread in position only, and all the members depicting different colors, they're all the same ranking vortex, exact intensity and size, but placed differently. So when the position spread is very small, so 0.1 here, it's a very linear situation. So the ENKF works perfectly, and you see that from the plus sign, you sample a very Gaussian distribution of the wind speed here. This is actually the radial wind velocity observed from the radar side here. When you start increasing position spread to slightly larger than 0.5 or even 3 times the size of the vortex, you see that first the distribution becomes skewed due to slight displacement, but the displacement gets larger, and now it's like very narrow instead of a typical Gaussian. If you do a moment matching Gaussian fitting, you'll find the dotted red line, and which is typically under or over exaggerating the distribution of the extreme values. So this case has been studied a lot by Chen and Snyder in assimilating wind position observation, and also by John Porter-Joy to test his localized particle filter. So I'm also using this exact same setup to test my MSA. So here's how MSA work, how it takes action. So first, I'm showing one of the members with very large displacement in gray here, and the true vortex is, of course, in the center. If I just apply the ENKF, the traditional algorithm, you find that with assimilating the observation at the plus sign here, you will have the new vortex more or less in the analysis, but the old vortex there's some residual of it because of the linear approximation. So you end up with the elongated shape of the vortex. Certainly you don't want that in your ensemble members. and the forecast certainly won't work very well. If I apply the multi-scale localization without the alignment step, so this is what I call MS no A, with 5 different scale components, you slightly, I'm not even sure it actually improves it, but it does discourage the highly nonlinear ENKF assumptions. So when ENKF deviates from the assumption, you start to see that the large scale component doesn't want to adjust as much as the original ENKF. But the actual MSA algorithm will reduce the problem of the nonlinearity on non-Gaussian prior distribution. So what happens is after the first large scale s equals 1 update, I have this very large, so the very coarse resolution image of this vortex being my prior, and the adjustment will be very linear. But from the linear adjustment, I compute the displacement vector Q here, showing in these arrows, to actually help me to move the prior vortex towards the center. So after that, I have a much improved prior for the second scale, and I do it again and again until the final scale. So I hope this is a very clear demonstration of how the alignment steps will help precondition the prior distribution to make the ENKF work better. So this is another look at the ensemble spaghetti plots of the wind contours, showing that when I start increasing the number of scales from 1 to 3 to 5, 7, it starts to approximate a nonlinear Bayesian solution. And I show the particle filter solution here to show that basically we're converging to, we're approaching something similar to a nonlinear solution. So to stress test the method, I draw 1,000 random trials, including the location of the observation and the prior positioning of the vortex, and summarize the behavior of the errors, first domain average error and also position errors of this posterior ensemble. I'm showing no DA in the gray and the traditional ENKF in white. And the blue ones are the MSA method with increasing number of scales. And finally, the dark green one is the particle filter. So first, you see that the particle filter is not actually the close to 0 error one, because when I randomly placed my observation in the domain, sometimes the observation is far from the vortex, and sometimes it's very close to the vortex center, meaning the observed wing is quite low. And there are some multimodal distribution or observation likelihood related to this case. Now, some of the prior members will accidentally be given higher importance weight because of just it hitting the low wind with a different angle. So the posterior mean of the bimodal distribution or multimodal distribution from the particle filter is not a good metric to showcase its performance. It's actually the correct Bayesian distribution, but just the mean is in the center of the 2 peaks probably doesn't make any sense. However, the multiscale alignment technique will still decrease the error because it's kind of converts the it transforms the observation into something else by decomposing it into large scales. So it does still collapse the prior ensemble onto one of the multimodal peaks. I'm not sure if that's still the best behavior you want to have in the ensemble filter, but it is for my case, it still converges to one of the correct peaks. I want to say. However, there are some issues when you do alignment by warping the model grid. First, the intensity error, it's not constrained very well. So the ENKF will certainly increase the intensity error because it just randomly puts some, it will just fit to the observation too much, and then you create a random wing maxima in your analysis. But the alignment doesn't help because you see that the error still increase even more than the ENKF when in the very, very linear regime. So the position error is very small in this leftmost side of the figure. This is because when we just try to illustrate here with the schematic here, So the blue one is the wind profile, and if you have the initial wind located on the discrete model grid, in the red dots here will depict a very nice vortex with the correct intensity, the wind maxima. But just shift it a little bit, not to the integer number of grid points, and maybe the wind maxima will end somewhere in between the grid points by the alignment method. And now you have this blue set of points, which means you missed the wind maxima by just because of the discretization of the model. It's actually not our fault, but actually the finite differencing model may have some issue with the representation of the wind. This is solvable by using maybe a Lagrangian approach to have the model grid following the sharp gradients in your system. But certainly in my paper, we haven't tried that yet. So this is one of the issues. The second issue is more severe, is that I try to test if my background flows are incoherent with my position error in the vortex, which means I put the background flow as a randomly drawn signal, which does not have the correct misplacement of the features. Then from the baseline to the incoherent background flow case, you see that my multiscale alignment performance is not as good. Because I am making a coherence assumption here that the vortex position error is actually part inherited by the large scale projection of their signal in the background flow. So this raises a question how to model cross-scale error relationships. So in typical work by the multiscale DA, you model a linear model, but you break the covariance matrix into multiple scale components. Now the off-diagonal parts are actually saying that the large scale and small scales are somewhat correlated. And my approach is actually saying that this linear method is not enough. I'm making the assumption that the position error in the large scale has the same component in the large scale. So you kind of have this off-diagonal term being through the displacement steps. But this is a little bit problematic when actually there's no correlation. So maybe if we can hybrid the two methods and trying to see if it fits more generic cases. So I'm reaching my time limit, I see.
Yeah, sorry.
So I will try to go towards my conclusion. Yes, so I've stress tested the multi-scale alignment, and there are some problems with the coherence assumption problem, and also the weakening of the vortex peak maximum wind. But we are trying to solve this. And there are also more challenges in the real application when we go to three-dimensional, and maybe we have some issue with physical balance. Yes, happy to take questions. Thanks.
Okay, thank you, Michael. That was a very, very interesting talk. There's two questions for you. First one is from Javier. For the cost function you showed, excuse me, how are the last two terms selected? Are there considerations of the underlying distribution of the alignment error, or is it more heuristic?
Heuristic, yes. I'm following what Sai Ravila put in their paper, that first you constrain the smoothness of the Q, so you don't want the displacement vector to jump around too wildly from pixel to pixel. So that's the first order thing. But I do see in the optical flow, so it's a computer vision literature, it's a different community. So they have tried a lot of different constraints, maybe divergence or vorticity. If you're working with dynamical fluid, so sometimes you want no divergence, or sometimes you actually don't want shear, for example. But I think that's a little bit not general enough, so I just stick with smoothness constraint for now.
Cool. This is okay. Thank you. Sounds interesting.
Yeah.
So Christo asks, nice talk, Michael. Displacement vectors can be derived easily for symmetric features like tropical cyclones. How easy is it to compute these quantities for asymmetrical but still well-defined systems, i.e. mid-latitude cyclones, where alignment consists of both translation and rotation? What about even more challenging, poorly defined intermediate intimate features like convective storms, where alignment becomes ambiguous?
Yeah, I see the point. It's actually I'm working on the very different kind of symmetry in my CIs. I'm currently working on predicting CIs linear features where means they crack. So these cracks are very one-dimensional in a two-dimensional field and multifractal actually. So it's hard to define. And also for wave patterns, it's hard to define the alignment whether you need to go left or go right to fit one of the peak. So it's a problem. I think this is also related to how you decompose your feature into different scales. For different features, symmetric ones, maybe a global Fourier space is enough. But for this very linear or maybe what they elongate in one of the dimension, like a front, sometimes you want to curvelet or wavelet decomposition of the scales. So I think if you decompose your independent parts in scales in your system correctly, then the alignment is actually very naturally follows that. Two independent features will align to their corresponding counterparts. But the problem is really difficult here. The difficulty is really here. You have a mixture of different signal, making the asymmetry happens, and that will make the problem very, very complicated. Sometimes I feel that even you want to not use some particular alignment to avoid issues, and maybe just use traditional nonlinear methods. Yeah.
Okay, I have to move on to the next speaker, but there are two more. There's a comment and a question in the Yopad. If you could please address them there, that would
Yes,
be
I
great.
can type my answers in the pad.
Okay, brilliant.
Yes.
If you can
Yeah.
stop sharing, that would be great. We can now move.
Yeah.
Thank you so much.